My name is Anton Chukhnov. This is my work with my colleague from St. Petersburg Electrotechnical University, Sergei Pozdniakov. This is actually not about the mathematics itself, but something about applying computer technologies in education and mathematical contests. So first of all, I'll speak about what's happening in our head. This is a psychological term, a psychological concept of the interiorization mechanism. When you perform some algorithm, when you only start to get acquainted with it, you perform it step by step, and you think about each step of it. But later, when we master the algorithm, we may say that we perform the algorithm automatically. For example, it's a very simple one. When we multiply, for example, 90 by 70 in school, in second class, you probably will start with multiplying 9 by 7 and then adding amount by zeros. But of course, none of us now don't do this step separately. We just say that we obtain 6,030, and that is all. So when we apply some algorithm, you may do it step by step and do it, perform it as a whole when it becomes completely understood by us. Also, also in the modern world, some parts of the algorithm which are not very important to understanding the problem, but given to the students in the contest, but are necessary to get the final answer, they can be now performed outside our mind. For example, in mathematical inputs, which are generally held in pen and paper form, everything is done by participant himself. But for example, the physics unimpaired, they are allowed to use a calculator just because for physics the calculations are not in the core of the task, but it's something supporting. And when we held the mathematical contest or informatical contest in the distant form, there is also room to bring some activity outside the human mind, and it allows to give the student more interesting tasks. Also, the computer, as we all know, is a powerful tool for experiments in mathematics. And when we hold a distant contest for students, we also may let them to do some experiments while solving the tasks. So the construct, test, explore contests, which are held by my colleagues in our department for years, it's about holding. It's generally about holding experimental tasks. So the students are given some mathematical model, and they solve some tasks, some optimization tasks, actually they get some environment and for this model, and they do some experiments. They try to build an optimal solution for some problem. There would be examples later. Also, we held an Olympiad in discrete mathematics and theoretical informatics. There are generally not the optimization problem, not the experimental one, but a problem that require a full solution for which we know the complete solution, and it could be obtained by students for the restricted time. Sorry. The most direct case of distributing some actions between the student and the computer is the case of Turing machine, which we use as well as this task we use as well as in our education process in the university, and also in distant contest and Olympiad in discrete mathematics and theoretical informatics. So there is some kind of trainer of Turing machine. The student writes program and the machine performs it. So the students see how it works. He or she doesn't need to perform the work of the machine in his head, but he writes a program for a Turing machine and he obtains a result. Before the end of the contest, the student doesn't know, of course, does this machine properly solve the task or not, but he at least can see how it works. Does it works as it intended by him? The next case is graph tasks. This is about. Oh, sorry. I think I missed the heading slide of this task. This is about this famous reconstruction problem in graphs. So it was formulated for students in terms of buttons connected with strings, but of course it's famous graph problem. Here we have a graph with 10 vertices, and we have 10 subgraphs obtained by removing one vertex for each subgraph. And there is a famous, well, actually it is an unsolved problem, but all mathematicians believe that for every graph we can restore it from its subgraphs obtained by removing y vertices. So to students, they were given 10 subgraphs with 9 vertices each, and they were asked to restore the initial graph of 10 vertices. So they may do something like that. So here we can see from the left side we can see a 9 vertex subgraph. The big one, we can choose every one of 10 to look at it in the big, not the small version. And from the right, there is a subgraph. There is a graph built by. Well, actually, it was built by me, but it's supposed to be built by students. And then we push button evaluate. And we see that this graph contains 2 subgraphs of initial graph, but not the whole 10. So there is another kind of feedback. Unlikely the previous one, where the student doesn't see the result until the very end of the contest. Here, he can see result immediately, and then he can try to improve his solution by doing something else with this graph. So what aspects of what has happened are here delegated to the computer? Of course, when we try to implement the graph task for students in this test, the concept of isomorphism is at least partially given to the computer, just because when the student draws a graph, he draws it not in some program for drawing. He draws it in our environment, and the moving vertices and edges from right to left and top to bottom doesn't change the graph. And there is a computer who cares for it. And also the final checking here is given to the computer, so the student doesn't need to check it at the end. So probably this is the main question which everyone should ask before giving the interactive task to the students. Should the task give the direct feedback about the correctness of the answer? The next problem which we implemented is another famous problem which has no effective algorithm as a whole, is a Steiner tree problem. If Clayton 1, we have a number of vertices. Well, I didn't say sorry for Russian interface, but here it is. We have a number of vertices. We can add here another vertices, and then we add some edges. And we need to build a tree on these old and new vertices of minimal total length. So actually this task could be divided by two ones. The first one is topological, we may say topological part, where we should add our extra vertices, which are gray here. And the second one is, the topological part is which would be the structure of the tree. And the geometrical part is where exactly should the new vertices be located. So it is known that every new vertex should be in the Fermat-Torricelli point of the triangle of three other vertices. And as we can see here, three, I should go to the next slide. What happens between these two slides? There was pressed a button, local optimization, and these vertices were moved in the optimal position. So we decided to get rid of the geometrical part of this task and to focus on the topological one. And the geometrical part was delegated to the computer. So we just asked student to put the new point where it should approximately be, and then the computer move the point where it should actually be. So the geometrical part of this task is not evaluated is not assessed by our system. Actually, yes. So only the topological structure is figure to be assessed. Well, so I think that's all. So this is just our thoughts about possible ways of distribution of the activity between student and the computer. The extra possibilities which computer allows us to give in distinct tests.